Hello everyone, welcome back. In this particular video, we're going to start talking about alpha carbon chemistry. This chemistry would lead to several synthetically useful reactions that result in the formation of carbon-carbon bonds. But before we jump into this chemistry, we have to first understand what is the alpha carbon. And then we will go into discuss what are enols and enolates. So let's get started with the alpha carbon, which sort of is the backbone of all of this chemistry. So the alpha carbon in a molecule would be defined as the carbon that's directly connected to the functional group in that molecule. Now, if you have a molecule with several functional groups, you would probably have several alpha carbons. That is a possibility. But if you're focusing on simple molecules, we can define it as the carbon that's directly connected to the functional group. So let's look at some examples. So if we start with an alkyl halide, let's say, in an alkyl halide, the halogen is our functional group. So the carbon that's directly connected to the functional group, that would be our alpha carbon. And then carbons connected to the alpha carbon would be beta, then we'll have gamma, and then delta. That's how the nomenclature works here. Moving on to an alcohol. Now I've chosen a different alcohol. The structure is slightly different, but if we have an alcohol, the functional group in this molecule is this hydroxyl group. And so the carbon that's directly connected to the functional group here, which is this carbon, that would be our alpha carbon. And now notice in this particular molecule, we have two beta carbons. And because there is symmetry in this molecule, the two beta carbons are equivalent. They're identical, okay? So they're both beta because there is symmetry in the molecule. Okay, moving on to an aldehyde. For an aldehyde, the functional group is this part of the molecule, the C double bond O with the H. So the carbonyl group with the hydrogen connected to it, that's your functional group for an aldehyde, which means the alpha carbon is this carbon, and then we have beta and there's gamma, okay? For an ester, the same would apply. Now, when it comes to esters, it is easy to get confused here because you might think that, oh, there's the acyl carbon, the C double bond O, and there's the ester oxygen, but these are carboxylic acid derivatives. So the focus is always on that acyl carbon or that group. So our functional group is this part of the molecule. Okay, these are all functional groups in these molecules. So that's our functional group. And if that's the functional group, and because it is a carboxylic acid derivative, we're going to say this is the alpha carbon, this is beta, and then we have gamma over there. Coming to a ketone now. Similar to an aldehyde, the functional group is the carbonyl group, which means you have alpha carbons here. Now notice for this particular ketone, we have two alpha carbons. This carbon on the left and the other carbon on the right, they are both connected to the carbonyl group, which is our functional group, which would make them both alpha. And additionally, notice how this molecule lacks symmetry. There is no symmetry in the molecule. So we're going to designate them differently. I'm going to say this is alpha and the other one is alpha prime to say that there are two different or two unique alpha carbons in this molecule. And then we'll have similarly a beta and a beta prime. And then we have a gamma carbon, but there's no gamma prime, okay, because that's just an ethyl group. So that's how you identify an alpha carbon, or what is the alpha carbon. Now let's look at another molecule which has more than one functional group. And let's see how would the assignment work there. Okay, so let's say if we have a molecule which has an aldehyde functional group in it, and additionally, there is a carboxylic acid in that molecule. Now, since there are two functional groups in this molecule, you're going to have two sets of alpha carbons, okay, or two alpha carbons here, one for each of the functional groups. So this is a functional group, and that's another functional group. And so as far as the aldehyde functional group is concerned, this is alpha. And as far as the carboxylic acid functional group is concerned, that's the alpha carbon for it. So for the aldehyde, we have alpha, beta, gamma this way. And in fact, this is the fourth carbon. So that carbon would be delta, alpha, beta, gamma, delta. And as far as the carboxylic acid is concerned, we'll have alpha, beta, gamma, and delta going in the opposite direction. So notice how there is a set of carbons for each of the functional groups that are involved here. So that's the introduction to the alpha carbon. Now that we know what an alpha carbon is, let's consider an alpha hydrogen. And once we understand what an alpha carbon is, it is very easy to pick out an alpha hydrogen. An alpha hydrogen is the hydrogen that's connected to the alpha carbon, or all hydrogens that are connected to alpha carbons would be alpha hydrogens. So let's look at some of these examples that we've already used. So for an alkyl halide, we have the functional group. So what we can see is, since this is the alpha carbon, we would have two alpha hydrogens here. There are two alpha hydrogens. For this alcohol, that's our alpha carbon, and there's only one hydrogen on it. So we have one alpha hydrogen in that molecule. For this carboxylic acid, we have two alpha hydrogens. For the aldehyde, that's our functional group in all of these cases. We have our alpha carbon, and so this would have two alpha hydrogens. And for this ketone, we have four alpha hydrogens, but they are different because they are connected to two different alpha carbons. So we're going to have H alpha and we're going to have H alpha prime. Now, why would these alphas be different from the alpha primes, or when would that matter? We will see those in later videos. But that's an introduction to alpha carbons and alpha hydrogens, both of which are very important as we track the formation of enols and enolates. And this is the chemistry happening at the alpha carbon in a lot of molecules that we'll be seeing. Now, in presence of a catalytic amount of an acid or a base, a carbonyl compound, which would include aldehydes and ketones, or a compound which has an acyl group in it, which would mean carboxylic acid derivatives, especially which has alpha hydrogens in it. So if these compounds have alpha hydrogens on them, they will exist in equilibrium with its enol form. Now, what are these enol forms? So let's look at a schematic here. Now, I've drawn a very generalized schematic here. I'm using a structure that would basically include or encompass all carbonyl and carboxylic acid derivatives. So if you look at the structure, if I replace that Z with a hydrogen, we're talking about an aldehyde here. If we replace Z with a carbon containing group, then we are looking at a ketone. Or if Z is a nitrogen containing group, we're looking at an amide. Or if Z is an oxygen with another carbon containing group, we are looking at an ester. So this is basically a very generalized structure here. But the key is this has a carbonyl carbon, or has a carbonyl group or an acyl group, and it has alpha hydrogens on it. So such a compound, when it is in presence of a catalytic amount of an acid, it would exist in equilibrium with its enol form. Now, the enol, the name, comes from the functional groups that are present in this molecule. So if you look at it, there is an alkene in this molecule, and there's also an alcohol part of the molecule. So that's why it's an enol. Now, when you have these two forms, they are referred to as the keto form. The keto form is the form where the carbon-oxygen double bond is there. And the enol form is where you have the carbon-carbon double bond with the hydroxyl group on it. Now, what's important to recognize here is that an enol is not any compound that has a double bond and a hydroxyl group on it. This enol here, this is specific. It is a vinyl alcohol, okay? It is a vinyl alcohol. That means the hydroxyl group is on one of the double bonded carbon atoms. That is very important for it to be an enol, okay? Now, this process of equilibration between the keto form and the enol form, this process is called a tautomerization, okay? And the two forms, the keto form and the enol forms, they're called tautomers of each other. Now, the same process can happen under basic conditions. So if you have a similar compound which has an alpha hydrogen on it, okay, then under basic conditions, it can exist in equilibrium with its enol form. And again, the enol is a vinyl alcohol. So that is very important. Any compound with an alkene in it and a hydroxyl group on it is not an enol. That's an important thing to remember. And this process, again, under basic conditions, it is still called a tautomerization reaction. And the keto form and the enol form are called tautomers of each other. Let's look at the mechanism of this tautomerization process, both under acidic and basic conditions. Under acidic conditions, this process starts with the protonation of this oxygen, the double bonded oxygen, whether it is an acyl oxygen or the carbonyl oxygen. So the first step involves a protonation event here. So with the acid, the oxygen will get protonated, and this would give us the protonated compound, lone pair positive charge on it. Now this protonated species that we've generated, this is resonance stabilized, so it can do resonance, so we can push that double bond up, and that would give us a resonance form where we will have OH, two lone pairs, Z, and a positive charge. So these are both resonance forms. And since we are under aqueous conditions here, this resonance form here can be deprotonated by water or any other mild base. And the electrons from this bond between the alpha carbon and the alpha hydrogen, so notice this hydrogen is the alpha hydrogen. So the electrons from the bond between alpha hydrogen and alpha carbon go into the space between the alpha carbon and this carbon with the formal charge on it. And that carbon was the carbonyl or the acyl carbon prior. So you get that, and which means we get the enol form of the molecule. And plus, we get the acid. So this process overall needs only a catalytic amount of acid because we regenerate the acid. Now the mechanism can also be written under basic conditions, although it will be slightly different. So that's our alpha hydrogen. And under basic conditions, the base, I'm using hydroxide here, but any strong base can do this. And we will look in more detail at what bases are best for doing these reactions, or what are requirements of a base to do this process. So a base can come and deprotonate the alpha hydrogen. That's where the mechanism would start, because we are under basic conditions. Simultaneously, the electrons here go to the alpha carbon. So this would bring us to the next intermediate, where we have a negative charge on that alpha carbon. Now, very similar to the case situation under acidic conditions, this intermediate that we've made, this is resonance stabilized. So you can do resonance on that intermediate. And the resonance is going to give us this form here, okay, where we have a double bond now between the alpha carbon and what was the carbonyl or the acyl carbon. So this is just resonance. And then again, under these conditions, this form here can get protonated using a proton source from the solvent, let's say water here, to give us the enol plus the hydroxide. So again, under basic conditions, this process is catalytic in base because we regenerate the base at the end of the reaction. So we make the enol under the acidic conditions. We can also make the enol under basic conditions. Now, the conjugate base of the enol, which is when you remove that proton, and that's this structure here, the conjugate base of the enol is called the enolate. Okay, so under basic conditions, the enol is in equilibrium with its conjugate base, which is the enolate. And both of these structures represent the enolate because they are just resonance forms of each other. So they are not different molecules, different chemical structures. They are just resonance forms of each other. So they represent the same molecule or the same species here. And so they are enolates. And notice how we do not come across an enolate species under acidic conditions. But under basic conditions, the enolate is possible. Now, both the enol and the enolate, they can behave as nucleophiles. So as far as an enol is concerned, a nucleophilic attack involving the enol would look something like this, where we can use the lone pair on this hydrogen and draw a resonance form where we have negative charge on that carbon. So if you look at it, the enol can serve as a nucleophile from that alpha carbon. Now, what's important to remember is this was our alpha carbon. So this is our alpha carbon. So the alpha carbon is nucleophilic in both the enol and the enolate. So that's the enol. Now, when you go to the enolate, you can do a similar thing where you can use that lone pair and push it down to that alpha carbon. Okay, so this carbon here is the alpha carbon, and we can write a resonance form where we have double bond O with a negative charge on the alpha carbon. So the alpha carbon can serve as a nucleophile in both the enol and the enolate, which means when you have an electrophile, you can use these electrons to attack an electrophile. You can use these electrons to attack an electrophiles. And this nucleophilic alpha carbon can be used for reacting with other carbon-containing compounds or other electrophilic carbons, like in alkyl halides or carbonyl compounds, and even with halogens. So you can do a variety of reactions here. Now, as far as the enolate is concerned, you would notice that the oxygen also bears the negative charge in one of the resonance forms. So these are basically resonance forms of each other, okay? So the oxygen also bears the negative charge. And nucleophilic attack involving the oxygen is also known, but it is much more limited than nucleophilic attack involving the carbon. So from an enolate, you can get an O attack, okay, where the oxygen is the nucleophile, or you can get a C attack where the carbon is the nucleophile. So both are possible. Both these attacks are possible in case of the enolate. The enol, for the most part, again, it also does a C attack. That's the most predominant form of attack, and it results in the formation of strong carbon-carbon bonds. Now, the position of equilibrium in a keto-enol tautomerism depends on the compound that we are considering, because there could be a wide variation. Now, for most regular enols, these would be compounds that contain just one carbonyl group. There's no other special features in them. It turns out the enol form is not the favored form. So if you look at it throughout here, we are looking at the enol form here. So this is the enol form, and this is the keto form. So for most regular compounds, the keto form is highly favored. Okay, it would exist mostly in the keto form and very little in the enol form. Now, certain factors can promote or stabilize the enol form. And this happens when the enol is stabilized, and there has to be some reason, some mechanism by which that enol is stabilized. Now, what example is the example of beta diketones? So these compounds are called beta diketones because if you look at it, if I consider one of these carbonyl groups as my functional group, then we have alpha here and there's a beta. So at the beta position, there's another keto group. So it's a beta diketone. Now, in case of beta diketones, the enol is favored. And that's because when the enol is formed, and again, notice the way we formed the enol is we removed one of the hydrogens from this alpha position and we moved it to the oxygen. We also converted the carbon-oxygen double bond into a single bond and a double bond between the alpha carbon and the carbonyl carbon. What was the carbonyl carbon before? So for this particular enol, there is a hydrogen bond that's possible between that enol hydrogen and the other keto group. And this hydrogen bonding stabilizes the enol form. So the H bond stabilizes the enol form. Apart from the hydrogen bonding, another factor which is crucial for the stability of this enol form is the conjugated nature of these double bonds. So there is conjugation present. Okay, that's another item here. So conjugation also stabilizes the enol form of that compound. Now, when we go to this next example here, what you notice is that we have phenol and its keto form. The phenol is the enol form of this compound. And in this particular case, as you can see, the enol form is highly favored. In fact, the compound exists mostly in the enol form, not in the keto form. And that's because the enol is again stabilized. The enol is stable because it is aromatic. So aromaticity is a big deal here. So that brings in a lot of stabilization, and that has to deal with the conjugated nature of these three double bonds, the planar structure, and all of those things that make a compound aromatic more stable. So what you see here is that there is a wide variation essentially in terms of the stability of the keto form versus the enol form. So for most compounds, although the keto form is stable, or it is the favored form at equilibrium, there are situations where the enol form could be favored. And it all depends on how much the enol form is stabilized when it is present in that particular form. In this part of the video, we're going to look at the choice of a base in enolate formation and how the choice of the base affects the equilibrium of enolate formation. And so just to review, An enolate is formed when you react a compound containing an alpha hydrogen with a base. And this can give you the enolate, which is resonance stabilized. So we are showing resonance over here. And what you want to remember is that both of these structures, they represent the enolate. Okay, they are both different ways of showing the enolate, plus the protonated base. So now the choice of this base is actually going to determine the position of the equilibrium. But it's not just the base. It is also the pKa of this compound that would determine the position of the equilibrium. So I'm going to demonstrate a few examples here to walk you through this. So let's assume that we have a simple carbonyl compound, let's say acetone. Okay, that's a ketone. I'm going to draw out one of these alpha hydrogens. That's what we're using. And if we use a base like sodium methoxide or sodium ethoxide, let's say sodium ethoxide, we're using a sodium alkoxide. Now this acid-base reaction is going to give us, the base is going to deprotonate, and we can put the electrons over here. So it's going to give us the enolate corresponding to acetone, plus it's going to give us ethanol. And the sodium ion here, that's going to be balancing this positive charge. So the sodium ion is here. So we get this. Now, the pKa of most simple ketones and carbonyl compounds, I would say these are somewhere in the range of about 19 to 20, like approximate numbers. They're about there. 19 to 20 is what the pKa of this alpha hydrogen is. So this is for the alpha hydrogen, okay, specifically for the alpha hydrogen. pKa for ethanol, this is around 16. So now if you look at this acid-base equation, then our stronger acid is on the product side. This is the stronger acid, whereas this is our weaker acid. And so what that means is this reaction should be favored in the backward direction, like that. Okay, so when you get to equilibrium, you will have some enolate present, but it will mostly be the carbonyl compound that is present. So you have the enolate that's present, but it would mostly be in the keto form that the compound is going to exist. So this is the enolate. Okay, so the pKa's help us determine what direction the reaction is going to favor. Now, I'm going to show you another example with a different carbonyl compound. Now, if it's a beta diketone that we are working with, so for a beta diketone like this, the most acidic alpha hydrogen is this one in the middle, okay? Because this carbon is alpha to both carbonyl groups. So that's the most acidic alpha carbon. And the pKa for this carbon is around 9 to 10 pKa units. And so now if you react this compound with sodium ethoxide, so we're not changing the base, we're still using the same base. Our product is going to be the enolate of this, which will have the negative charge here. So that's our enolate. Now, recognize that this structure of the enolate doesn't look like the enolate. It's only the resonance form of this, which looks more like the enolate, okay? But because it's just a resonance form, it is still the enolate, plus ethanol now. And pKa for ethanol is around 16. So that means in this particular case, when you have a beta diketone, sodium ethoxide is actually a strong enough base to push this reaction in the forward direction because the stronger acid is now on the reactant side, not on the product side. So the reactant, the beta diketone, is a stronger acid than ethanol. And so this reaction is actually going to favor the enolate. So we will be able to make a sufficient amount of enolate. In fact, almost complete enolate formation is going to happen because of this huge difference in pKa. And we will have almost complete enolate formation at equilibrium. So then the question is, okay, so for simple compounds like this one, how do we deal with those, right? What sort of a base should we use? And the answer is we can use other bases. For simple carbonyl compounds, to push the equilibrium of the enolate formation towards the product or in favor of the enolate, we can use other bases like sodium hydride. Okay, this is sodium hydride, or lithium diisopropyl amide. So when you react a simple carbonyl compound like a ketone with sodium hydride, you're going to get the enolate and you're going to make H2, hydrogen. Now, one advantage to this process is that hydrogen is a gas. So it's going to escape from the system. And so that would push the reaction forward to a complete conversion. Okay, so you will go completely to the enolate. In fact, there should not be any equilibrium here because your acid, your conjugate acid just escaped from the system. Now, even if that did not happen, the pKa for these compounds, as we know, they are in the 19 to 20 range. pKa for hydrogen is around 35. So even if it were to stay, because of this vast difference in the pKa's, this reaction is going to be favored towards the product. Our stronger acid is on the reactant side. Okay, so the pKa would be favored for the formation of the enolate product here. Similarly, lithium diisopropylamide or amide, which is a nitrogen-based base. Okay, so the negative charge is on the nitrogen. This would push the equilibrium in the forward direction towards the enolate because the amine conjugate acid that's formed, it has a pKa around 36 or between 36 and 40 is where the amines are. So again, the stronger acid with a lower pKa is on the on the reactant side, sorry. And so the product, the enolate, would be favored under these conditions. So we have a few options here. So based on the pKa of your starting material, you can choose an appropriate base to push the reaction forward and make your enolate, okay? So the position of the equilibrium really depends on the pKa of your starting material, the alpha carbon compound, and on the choice of the base. That would determine the position of your equilibrium. I hope you find this information useful. Bye.